Stefan Fassbinder. Now, who is the German Copper Institute? We represent the copper industry in Germany, Austria, and Switzerland, and we give free advice and consultancy to everybody who has any queries in the coherence of the application of copper and its alloys, and I'm in charge of the electrical applications. And quite obviously, cables are an electrical application. Now, there are certain sites which with enhanced requirements for safety and security, and which we don't like to ever look like this picture here, which was taken in 1996 when we had a dreadful fire accident at Düsseldorf airport. Our office is also based in Düsseldorf, and so this was roused some emotions also among us, because no fewer than 17 people were killed during this accident. Now, it is never ever possible to absolutely avoid the breaking out of a fire, but if it happens, then we want to rescue as many lives as possible. For these reasons, the electrical installation in such locations also has to comply with certain special requirements, and among these also the components, say the cables, have to fulfill certain special requirements which go beyond those for the normal standard generic requirements. So a fire resistant cable or fire retardant cable, it has to have fire retardant insulants, as the name says. It has to less fuel the fire than a normal cable would. The entire fuel energy content per square meter of such a building is limited by standards and laws, and it has to expel as few toxic gases as possible if a fire occurs. And prior to all, it needs to remain functional for a defined period of time. Now, the standards that standardize such cables obviously have two gaps. The first is that it is somewhat unclear which cables are really fire resistant and which the fire conditions are like. It is a bit difficult to make a test fire in a test rig, and the conditions under which such cables are tested are a bit lenient. They are exposed to flames and fire of a certain temperature, yes, but no debris falling off the ceiling or so. This is not tested. Actually, the normal plastic insulated fire retardant cables that we normally use become so brittle, at least the insulant becomes very brittle and it is practically burned out, that when debris falls on it, there will be not much left of it than a short circuit. The second gap is about the resistivity of the copper, because in copper, like in all metals, the resistivity increases, say the conductivity decreases at elevated temperatures. Experts say about the so-called fire retardant cables, well, they all burn sooner or later, or at higher temperatures, maybe slower, or maybe self-extinguishing, but if there is a fire, if they are exposed to a fire, they also burn out. This is the general problem. The cables are complete with improved properties under fire conditions, they are called in the standards, and they are hence just somewhat better than ordinary PVC cables, but not really good. This is simply not possible to make out of plastic material, insulants. But they are many times more expensive than ordinary PVC cables. Now, in fact, there is an alternative available, of which I hear very little speak. They are rather unknown in some countries, and others they are quite popular, and that's mineral insulated cables. They consist of copper conductors copper melts at 1083 degrees. The insulant is magnesium oxide. Its melting point is at 2800 degrees, and the outer sheath is made of copper again. Nothing else, no other material involved in the whole cable, just these two materials. And these cables are in fact capable of surviving a fire, not just sustaining their functionality for a limited period of time, but if they are exposed to a smaller fire accident, actually the cable can remain in place and remains operable for years after. It is not really damaged. Because they are absolutely uncombustible. They are extremely sturdy and robust, mechanically strong, and as I said before, they even survive a fire rather than just to sustain their function for a limited period of time. And they even come at a lower price. They are somewhat more expensive than a so-called E30 cable, which is supposed to remain functional for 30 minutes in a fire, but they are even a bit cheaper than the E90 cable, which is supposed to remain functional for 90 minutes. And on top of this comes another advantage, namely that they save some space. This is the diameter of a normal cable, and going to the mineral insulated cable, first of all, the volume of insulant is smaller here, and secondly, you can save one conductor, because the outer copper sheath can and even should or must be used as a PE conductor. It has to be earthed anyway, for safety reasons and for EMC reasons. So at the same time, this outer sheath will replace the PE conductor with the protective conductor in the cable, and both effects together make the cable quite a bit smaller than a normal fire retardant cable is if it has the same current carrying capability. On top of this copper sheet has about 2.5 times the cross-sectional area that a normal PE conductor has, and therefore the EMC capability as well as the electrical safety is much better than in an ordinary cable, because at the same time it is also a screen. It works like a screen, and the whole cable can be used as a shielded cable. When I first came across them during my first years with Deutsches Kupferinstitut, I was invited to BICC in Manchester and for a performance. Nowadays the company BICC does no longer produce them. They sold this business area, but at that time they were quite busy here and made a very good test and demonstration rig where you could convince yourself of the capabilities of this cable. You can even hammer on it, and you really have to hammer it very hard and for quite a long time before a short circuit really occurs. Then they give you the same hammer and a normal plastic cable, and you just tick the cable slightly and the cable fails. An incandescent lamp is connected to it to indicate the moment when it fails. Another drawback in the standards for mineral insulated cables is that they are obviously measured with stricter measures than a normal plastic cable. So for commonplace so-called fireproof cables, it says in the standards, or at least in some of the standards, that they are not appropriate for installation underground or underwater. Differently from that, mineral insulators are required to be immersed into water for at least 1 hour before they are tested. Now this, I think, is a different test condition for a product that should normally cover the same range of application and serve the same purpose. There is quite a number of different size and cross sections of mineral insulated cables available from one conductor up to 17 conductors. You can have them. You can also have a special cross section that has a second screen inside here. If you look at this one, so one could be earthed, one could be insulated, or whatever you like. The installation technique of such cables is nothing more difficult than with ordinary cables, is only very different. So, for instance, you need special cable glands, and for fixing these cable glands you need a special tool. And fixing this and using this special tool also requires special skills, but normal installing a normal cable also requires special skills. And since it is under the bottom line nothing more difficult to use mineral insulated cables, you either have to learn this or you have to learn that. One difference is that they are very pliable, but they have a plastic behavior, this plastic behavior of deformation, while from normal plastic insulated cables you expect an elastic behavior. But this is nothing more, nothing less difficult to install. It's just different. You must only make sure that you don't bend the mineral insulated cables to and fro too often, because on account of the work hardening process which all metals undergo, they will become harder and harder, and finally they will break. So first attempt installing them, bending them, should always be successful. Beyond this, there is only one disadvantage which you have to cope with, that is that the conductor marking is not there. It is simply not possible to mark a conductor with a cable that can run at a temperature up to 1050 degrees Celsius. With the PE conductor it is evident. Here you see it. Hello? Here you have the PE conductor, and it is already marked as such, and it is connected to the cable gland and hence to the cable screen. This is logical. The other conductors they are not marked and have to be identified electrically, but this is also the case with some other plastic cables. Sometimes you have a cable which has only black conductors in there, and or at least several ones with the same color. Another opportunity or advantage or range of application for mineral insulated cables is in the fine arts, in historically relevant buildings, because for the first, the cables are thinner, and secondly, their natural copper color often resembles very much the background on which they are mantled. So these actually are cables. Here they are still fairly easy to find, but find them here, it's not so easy. Now where's the cable? Here, there's one here, here's one, and here's another one. You wouldn't suppose it. And this one is really difficult. Can you find a cable here? Yeah, there is one. Believe it or not, but this here is a mineral insulated cable. It is used here, maybe not really for safety purposes, maybe also for safety purposes, but in the first place for their good looking or their unobtrusive look, which aligns with the art objects here very well. Now, the second problem with the fire retardant cables is the conductivity of the copper, because, as I said before, it is temperature dependent. Now, this rouses two concerns. For the one, the voltage drop in a cable increases under fire condition when the cable is exposed to an elevated temperature. And when the ambient temperature rises is considerably above the usual temperature, then also the cable over temperature above the ambient will increase considerably. The former issue is dealt with in the standards. The latter one, unfortunately, is not, and this is a gap. Let's look at first at just a side issue of this second issue. The calculation of the temperature out of the resistivity, or the resistivity out of the temperature, can be done by different formulas. I have found no fewer than 4 here. The first one is usually used for calculating the temperature rise in windings of reactors and small transformers, sometimes also motors. Normally it is written in this way, like the third formula, which is just a conversion of the first. You see that the alpha coefficient which we have in here, that may look familiar to you, and this x coefficient in the third formula may look less familiar, but the x coefficient is only the inverse, the reciprocal of the alpha coefficient. So this formula is the same as this one. This one is used in the EN 6742, which deals with the safety of reactors and small transformers. It's these two, the two blue formulas are linear formulas, and they neglect that the change of resistivity of metals, of copper specifically, has a second coefficient in there, which goes in by the square of the temperature, like here. The beta coefficient, as you see, is very small, 0.6 ppm, and hence it has practically no effect in the range of normal operating temperatures of, say, a motor, a transformer, a reactor. But it does have when we speak about fires. This formula, the yellow one, is an exponential approximation of the second formula, which works as such pretty well. If you look at this, this is the change of resistivity plotted on the abscissa here against the change of temperature on the ordinate. Now, in the range of normal operating temperature of electrical devices, the differences calculated with the 3 different formulas is not significant. But if you go up in the range, this is the point from which the formula starts. But if you go up in the range to fire conditions, and standards assume an ambient temperature between 650 and 950 degrees Celsius for a fire, then you see that the linear formula does no longer yield precise values. It yields too low values for the change of resistivity in copper, while the other two approaches, the one including the beta coefficient and the exponential formula, align pretty well, lead to nearly the same results. This is again the point we start from, and this is the point which we are now dealing with. You see that with an ambient temperature of 950 degrees as assumed by the standards in a fire, we have 5 times the resistivity in copper as we have at room temperature. So the main point of issue number 2 is the conductor temperature rise. With the ambient temperature rising from say 30 degrees in normal operation to 950 degrees in the case of a fire, the resistivity of copper rises by a factor of 5. Normally a cable is assumed to operate at an ambient temperature of 30 degrees, and on account of the ohmic losses, the temperature rise is assumed to be 40 Kelvin, so that will land at 70 degrees Celsius for the absolute operating temperature of the cable. Well, this has two effects. This increases the voltage drop, and it also increases the heat generated in the cable. The first point is taken into regard by the relevant standards. The second one, unfortunately, is not a single standard. Yes, one standard makes a statement here. That's the national standard of Belgium, of a relatively small country, which at least points out that the change of heat dissipation has to be taken into account. Because note that according to the standard, these cables, be they mineral insulated or standard fire resistant plastic cables, are tested without load. There is just an incandescent lamp connected to indicate the moment and the temperature when the cable fails, to decide whether it passes the test or fails. While when the cable is running, is being operated at its rated load, then you must consider that if the normal temperature rise above ambient is 40 Kelvin, then under fire condition the temperature rise would be 200 Kelvin, because as we found out, the resistivity of the conductor material is 5 times as high as at room temperature. And this fact is not taken into regard by the standards. This is really a gap. The standards only take into regard the voltage drop in the cable, because you have to make sure that you still have the minimum voltage available at the end of the cable, but the standards assume that only a fraction of the entire cable length is exposed to the fire, maybe 1/5 or 1/10 of the cable. This is justified because normally such cable will be several hundred meters long and run through several rooms, while there will probably be a fire only in one room. And so it is absolutely legitimate to calculate the voltage drop only for a fraction of the entire length. But regardless of the length exposed to a fire, be it only 1 meter, then this 1 meter will start to melt. The conductor temperature will then be 1150 degrees if you assume 950 ambient, and at 1083 the copper already melts. About other metals we don't even need to speak at this point. They aren't allowed anyway for such cables. This leads us to the conclusion that all the relevant standards in the different countries and also at international level require an upgrade, because in principle a fireproof or fire retardant safety cable, be it mineral insulated or standard, never mind, would need to be designed with 5 times the cross section the standard cable for the same current rating would need to have. This is a bit exaggerated, of course, and in practice a compromise needs to be found. Standardizing bodies, I think, will have to do something about it. anyhow, whatever your decision is, whether you take, say, 2 or 2.5 times the standard cross-section, a mineral insulated cable will always be the far better choice and not necessarily the most expensive one. The problem is sometimes where to get them from. For instance, back home in my country, in Germany, they are not produced. At present, I could spot 3 manufacturers of mineral insulated cables, but for sure this list is not complete. There are more available. The first one, which you'll see listed here, is also a member of ECI, of the European Copper Institute, and so it is natural that we first of all support them, but other manufacturers are also available. The Rexam Mineral Cables, to my knowledge, is a dedicated specialized company which only produces this type of cable. While Tyco, you probably know Tyco, is a big company which among others also offers this product. And as I say, if you browse the internet, you can find more, but it may happen that when you buy with another source, you still land with the same producer and you don't realize it. The market may be a bit sophisticated, and about this I cannot say anymore. I can only give you the recommendation: be careful when selecting cables for fire safety, fire hazardized, jeopardized areas, and make sure you select a cross section somewhat larger than would normally suffice to satisfy the standards, because the real fire is different from what a standard fire is supposed to be, and if ever possible, the far better choice is mineral insulated cables. Thank you very much. If you have any queries,
Okay.
welcome.
Yes, Stefan. Okay. Okay, so thank you very much, Stefan, for this interesting presentation. So now we invite our audience to submit their questions through the window Submit a Question. And
Nothing there so long.
uh, yes, so please do feel free to go ahead and send your questions. So let me check.
Fernando, look, they erratically entered some question in the present window. Let's have a look.
Yes, so
You have to earth the cable on both ends. This is a question uh, regarding EMC. That is not a question of the cable itself. That depends on what you use it for. Most of the mineral insulated cables are energy cables, power cables, and then earthing at one end will be enough. But there are also signal cables available, um, and then it depends on the frequency and the length of the cable, whether you need to earth them at both ends. As a rule, I would say then in that case you would, yes, you would have to earth them at both ends as you do with a shielded cable. The bending radius, actually, I don't know. It depends. What this is specified when you collect technical information about this cable. You can find the bending radius. It may vary with the diameter. It need not be the same factor, diameter by bending radius, for each cable strength. And the demand in future for crystalline wafer and granular, this I don't understand. But what?
no, no, actually, I'm sending to the main pod on the top of the window the relevant questions. So the next question is major problem in standards followed for selecting the cables for fire circuits. What can be done? Can ICA help us?
Major problem in standards followed for selecting the cables for fire circuits. Yes. What can be done? Well, simply to go beyond the standard, because in the end, a standard, an electrical standard, is not a law, and standard standardizes what is the minimum requirement for average application. If you have enhanced requirements, then you must go beyond the standards and specify more than this standard minimum. So as long as the standards are so lenient as they are at present, and modifying standards takes decades, then I can give no other recommendation than to keep in mind what I said about the conductor heating, and use larger cross sections, and if ever possible use mineral insulated cables.
Okay, next question. About end items like smoke detectors, motor control centers, motors, etc. If these cannot survive the fire, what's the use of cables? How do you compare with FP200? Thank you.
What is FP200? The protection class? Probably. Um,
Well, let's ask to Sunil to precise what's exactly FP200. So please you can
well,
submit.
as I said, the smoke detectors and so on, the motor control and all these devices may be located in a different room that is affected by the fire. When the cable passes through one room which is affected by a fire, then you already have the problem. And you, you have bad luck if all the rest is also in that room, but you have a very good chance that only the cable is affected by the fire, and not your equipment. So in these cases, it does help.
Okay. In the meantime, you have the precision for FP200.
Yeah, yes.
It's a fire-rated cable for 9 hours.
Um, well, the answer remains the same as I said. The device that is powered or supplied by this cable need not necessarily be affected by the fire. If so, then of course the whole thing is not of much use.
Okay. Okay, very well. So next question. How new is the application and what is the market response level of demand?
The application is very old. The principle of the mineral insulated cable was invented already before the Second World War. In a period during the and shortly after, when the out made of aluminium for shortage of copper, but that is of course not so good because it melts 660 degrees. The market response is very different depending on country. The mineral insulated cables have quite a long tradition and have a fixed market sector. Uh, in Canada, and I suppose also in the US. In other countries, they are in Germany, for instance, they are nearly unknown. We have more questions at the bottom.
Yes.
Installation.
So, do you know if magnesium oxide resistivity varies when the temperature rises?
Where, where did you go? No, one. one question vanished from my screen. I have still the question about theft on my screen.
Yes, but please refer to the ones that I'm sending to the main post of submit the question.
Yes. Okay.
So the last one is, do you know if magnesium oxide resistivity varies when the temperature rises?
This I don't
Thank you.
know, but I suppose that it does, but the resistivity will still be in such a high range that it plays no role. Otherwise, I would have heard about it. But the certain creepage or leakage current through the insulant, I have never heard anybody talking of. So this obviously does not practically exist as a practical problem. Now, about the theft, well, I don't know what to do against theft, but this is a general question which always applies to all cables, especially if they are made of copper. We have had a copper price surge in, when was it, 2008 and 2009. Copper went above €7 per kilo, and then copper was stolen everywhere, and there is little you can do. This is not specific for certain types of cable. Glass and PVC connectors on insulated cables affect fire rating. What about the joints? These are a specific question, I think, which have to be directed to the individual supplier. There are suppliers for this material, and they specify, they give precise ratings for their material.
Okay, very well. Thank you very much, Stefan. So it seems that we have no more questions till now. So thank you very much, everybody, for your participation. Thank you, Stefan, for this um, brilliant and quick speech on this topic.
That was welcome.
I hope that we brought light on this topic to our audience. And well, please come back to Leonardo Energy website where we will publish soon the recording of this webinar. So, Stefan, you have the floor to adjourn. Thank you.
Thank you, everybody, for your attention, and would like to be in contact with you again. Bye bye.